Hi everyone, welcome to this SIGGRAPH technical paper session about modeling and optimizing cone joints for complex assemblies. My name is Ziki Wang and I'm a PhD student from EPFL. This is a joint research work between EPFL and SUTD. An assembly refers to a collection of parts jointed together to achieve a specific form and functionality. This project is motivated by the recent development in digital fabrication, particularly the automatic timber assembly. The goal is to use robotic arms to assist timber structure assembly. The structure should be stable and assemblable at every intermediate assembly stage as well as their final stage. Interlocking joints are used to connect adjacent beams to provide structural stability. Assembling beams connected with tight single-direction joints is difficult and require high assembly precision. Currently, the structure design and assembly planning still requires a huge amount of human work. Therefore, given an unstable assembly with planar contacts and assembly sequence, we propose a computational method utilizing cone joints to make the optimized assembly to be stable and easy to assemble. Several challenges need to be addressed in this project. First, how to select the appropriate joint for each contact. The joint stability is measured by how strict it is immobilized the relative movement of the two associated parts. The joint assemblability is measured by all collision-free translation motions that separate the two associated parts. We focus on the translational assembly and disassembly motion since it is commonly used and easy to execute. For a planar joint, it has the strongest assemblability but the weakest stability. The four-parts model is not stable. For a single-direction joint, it has the strongest stability but the weakest assemblability. The four-parts model is hard to assemble. Thus, we propose to use the cone joints, which interpolate between planar and single-direction joint, such that this four-part assembly can have a good balance between stability and assemblability. Please note that planar and single-direction joints are special cases of cone joints. The second challenge is about dividing the hard-to-solve global problems into easy-to-solve local problems. Optimizing structural stability is a global problem. In this animation, the energy function E reaches zero if the assembly is in equilibrium under gravity, otherwise the assembly is not stable. Any change of the joints could influence the structural stability of the assembly. Optimizing part assemblability, however, is a local problem. The cone at the right shows the orange part's assemblability. The orange part's assemblability cone is only affected locally by the two edges highlighted in purple. The angle of the cone has to be larger than a user-specified number alpha. So what we propose is to replace the previous part geometry-based equilibrium test with an abstract motion-based equilibrium test, which does not rely on the part geometry. Then our kinematic design stage optimizes this abstract representation to make it stable and easy to assemble, which is followed by a geometry design stage where we decompose the global stability problem into small local problems for each contact and solve it efficiently. Here shows a stable and easy to assemble frame structure connected with cone joints. Our method can also make the assembling process easier by making the assembly stable at each assembling step. Our method can optimize structure to obtain more tilting stability. The igloo can be tilted for at most 35 degrees before collapsing. Thank you.